Hello, this is Logan Chipkin, and you're listening to the Fallible Animals podcast. Today I have another interview that I had conducted a few months ago, this time with science writer Graham Farmelo. Graham Farmelo is a former academic, and he's now an award-winning biographer and science writer based out of London. He's written books such as The Strangest Man, which is a biography of physicist Paul Dirac, and The Universe Speaks in Numbers, which is the subject of our discussion today. The Universe Speaks in Numbers is a historical account of the relationship between math and physics as perceived by practitioners in both communities of math and physics. In our interview, Graham and I talk about the relationship between math and physics, the greatest discrepancy currently plaguing physics, whether the laws of nature are invented or discovered, and many other very interesting topics. Graham is both charming and very knowledgeable about the history of how these subjects intertwine and when they came together and when they were further apart, and also he knows a lot about the physics itself. We talk a little bit about string theory and other ideas that we really haven't covered before on the podcast, but it's all very accessible. Aereo magazine actually published a shorter and edited transcript of the interview, so if you want to read that in addition or instead of listening to this interview, I will link to the transcript down below in the show notes page. I'll also link to Graham's website as well as a link to where you can purchase his book, The Universe Speaks in Numbers. I really recommend the book if you ever just want to learn about the history of ideas, as I sometimes talk about. This is a great book for just that. By the way, before I forget, if you ever want me to interview someone in particular, whether it's a writer or a thinker or a scientist, definitely let me know. Tweet at me or contact me in some other way. My Twitter is @ChipkinLogan. And definitely let me know what you think, because I'd be happy to follow up with anyone who's doing interesting work or thinking about subjects that you and I would both find interesting. I look forward to hearing who you have in mind. And finally, the same two caveats apply that applied last week. A, this interview was conducted before I had a microphone, and B, I was never going to publish the audio, and so it comes off as a formal interview more than a discussion. And without further ado, I give you Graham Farmelo. So in your book, The Universe Speaks in Numbers, you write at one point that we will never know whether the laws of nature are invented or discovered.
Yes.
So, okay, it seems to me that people have made similar claims about other phenomena or regularities that we observe in nature. What is it about this particular problem that you can say with confidence that we'll just never know the answer?
I don't see how we could know the answer to that. I think there are two parts to this. Mathematicians have discussed for centuries whether they're looking at an invented structure or a discovered structure, whether it pre-exists out there, ready for them to find, or whether it's an imaginative construction. And you can find brilliant mathematicians on both sides of that question. Now, it's very similar in physics. There are, I think it's fair to say, most physicists would say that there are fundamental laws of nature out there that we can discover, right? They're out there, right? In some perhaps mystical sense. Other people say, especially critics of some aspects of physics, say it's a construction, it's a human construction. I don't see how that can ever be demonstrated one way or the other, in both senses, for either mathematics or to physics. A definitive proof, so to speak, that one of those two stories is right. So that's what I meant by that. But there are strong views on both sides.
Yeah. I think any question that is interesting enough is answerable in some way. We just might not have the right framework yet, but because we can't really predict the future of knowledge,
Yeah. I must admit, my own personal belief is I like most physicists. I mean, I'm talking here about physicists way out of my league. But, the idea that this is all a kind of grand human fabrication, I find very irritating. I mean, I really think that is far too much of a stretch for me to take on. But to say that, somehow to say that people, to express a belief that those things are out there, is also a bit mystical for me. I mean, it's a difficult, physicists these days, they tend to avoid these philosophical disputes. Most of the discussions that we're having now might be had over a coffee bar, over a coffee, or late at night, but they're not something that I think preoccupies a lot of physicists. Whereas back in, for example, the days of Einstein and Bohr and further back to James Clerk Maxwell, these were really central issues. People really did take this extremely seriously. So I think it's fair to say that modern physicists are purposely less philosophical than their predecessors a few centuries ago. I think that's a fair statement.
Yeah, I think so too. I think it's become, as you talk about in your book, sort of more mathematical and less philosophical.
Well, I don't know. I just like to take issue with that a little bit, because remember, the guy who, in a sense, began the modern project, which was Newton, right? He was mathematical. He's one of the greatest mathematicians, right?
Yeah.
But he saw himself as a natural philosopher. That's what he believed himself to be.
That's right.
He believed, and what by that he meant that he was somebody engaged in the rational pursuit, or the rational quest to understand the creation of God.
That's right. Yeah.
That's what he believed, right? And the idea that this mathematics was simply a description of the world without God involved in it would have been anathema to him. So that's why, if I may, I pick you up slightly on that. But I think it's worth noting this is not that long ago in the course of human history. But yeah, but we're agreed that what we're doing now is God does not have an essential place in it. I mean, there are some theoreticians who are religious; they do believe in God, but it's not something that is discussed as part and parcel of the package, as it was with Newton, for whom it was everything.
Yeah, I hear you. I guess I personally, and this is my own view, is that I wish some physicists would recognize that philosophy seems to, at least historically, is always intertwined with whatever progress is being made in physics. There's always some philosophical component, and it always radicalizes or enhances our worldview. And so I don't know if that would just cease just because it seems like maybe it's easier to work on math rather than...
Yeah, it's a good point. And, I must say, I'm not completely anti-philosophy, crudely speaking. I mean, I have friends who are philosophers of physics, and they're really smart people, and they make the case. My friend Michaela Massimi at the University of Edinburgh, I interviewed recently, and I think she's right that philosophers look at questions about the nature of physics that could well become increasingly important. For example, if a perfectly sensible person says to physicists, well, what exactly are you aiming to do here? Why should we invest in this subject rather than that subject, right? And then they look at these screeds of work that they cannot possibly understand, right? Then within seconds, you're into philosophical territory.
Yeah, exactly.
And, I think that philosophers have a place in that, right? I think a mistake that I would respectfully suggest that some physicists make is that they criticize philosophers because they think, well, this can't help me do my physics, right? And therefore it's irrelevant to me, right? And I know very smart people who are impatient with it. You don't know that Stephen Hawking said that philosophy is dead. There are other instances of this kind of thing. And I really do think we should be a bit more respectful of not just experts in our own field, but people who comment on the field knowledgeably and constructively.
Yeah, I mean, the scientific method itself is arguably a subset of philosophy. You can't use science to justify the scientific method, I don't think. That's circular logic, I think. So, all right, if we may move on a little bit to something more concrete. So in your book, you talk a lot about the different philosophical approaches that Einstein and Dirac had, which I thought was fun to read. So with hindsight, or just a few decades, but still a lot of hindsight, which of their philosophies do you think has been more fruitful? And if you wouldn't mind maybe describing what that philosophy is for the reader.
Yeah, well, Einstein came to, in the latter part of his career, he came to believe that the royal road to discovering fundamental laws of nature was through mathematics. He got that view from his development of his theory of gravity, which was a monumental achievement. There can be no denying that. In his youth, which was spectacularly successful in physics, he really did believe that physics is essentially a down-to-earth science, that you didn't need fancy mathematics to do it. And he skipped his math classes, and he really didn't pay much attention to it, to advanced mathematics. During the development of his theory of gravity, he came to see that he could not set out that theory in a coherent way unless he used advanced mathematics, in that case, differential geometry, which was sitting on the shelf waiting for him, as he found, just ready to use, like he was an explorer going into completely unknown territory, and he had a complete toolkit that enabled him to solve the problems of exploration, which was, it looked like something like a miracle for him, right? And in the final stages of completing that theory, this is in the late fall of 1915, he really did believe that mathematics had guided him to those final equations, which most people think is the greatest achievement of his life. Now, that carried on, that belief in the value of mathematics carried on, because he tried to extend that theory to include electromagnetism as well, so that he had what he called a unified theory, not just of gravity, but of electricity and magnetism as well. Now, the problem was there were no experimental clues that could help him along the way. So what he believed was that by developing the underlying mathematics of his theory, he would be able to find a way of extending it to electromagnetism. Now, I think that although that, in my judgment, that agenda was doomed to fail because he ignored the quantum theory and the experiments that partly led to the development of that, nonetheless, Einstein had made an important point, which is that mathematically rich theories like his theory of gravity, by developing their mathematics, that can lead to progress. So I would say that Einstein was ahead of his time. He didn't deserve the ridicule that he got from people like Wolfgang Pauli, who was accused him of basically becoming a pure mathematician, of trying to work with a completely squeezed out lemon, as Pauli put it about Einstein's classical theory. But I do think he made a valuable contribution there. Now, if you turn to Dirac, then I think he was, as you often hear people say today, he was the first truly modern theoretician, otherwise described as the theorist's theorist. He, in my view, was way ahead of his time. He was of the view that physicists should attend to mathematics and mathematicians should attend to physics, because in his view, and I'm not quoting directly here, but it's close enough, mathematics is a game in which mathematicians invent the rules. Physics is a game where nature supplies its own rules, and it's our job to try and guess them. And furthermore, we constantly find that the mathematics that the mathematicians are studying at the frontiers is exactly the kind of mathematics that the physicists find at the frontiers as well. So that he's arguing that there's a common cause in physicists and mathematicians working together. Now, that has proved a very prescient observation in my view. Remember, he experienced that when he was discovering his law of gravity. That's pretty well exactly what he found. Today, you look at leading mathematicians and leading physicists, there's a huge area of overlap where the physicists find themselves doing cutting edge mathematics, and mathematicians find themselves getting guidance and insights from the world of physics. So Dirac, in my view, was way, way ahead of his time in pointing towards that.
So basically they were both ahead of their time.
Very much so. But I think, as I said, I'm not kind of giving points for, who's the greatest physicist or who. Einstein, in my view, was preeminently the greatest physicist of the 20th century. But I do think that insight of Dirac's proved to be extremely prescient, right, for the way we're working now. Now, you'll know that some people think that this mathematics has got out of hand, that physicists have got too interested in mathematics, it's misled them, and what have you. Now, I respectfully disagree with that. I think that we're in an unusual time, at least in my lifetime in physics, because the number of really good new clues from nature has slowed down. In the last few decades, there have been relatively few really juicy clues about the way that theoreticians should develop their theories. Instead, what theoreticians have done is, just as we said with Einstein and Dirac, they've developed the best theories that we have and found themselves on the territory of mathematics. Now, there's one very, very important point to make about these speculations, that the great work that is being done now in theoretical physics is to a very large extent based on the two foundational theories of 20th century physics, which is the basic theory of relativity, right, and quantum mechanics. Now, relativity, much of it was pioneered by Albert Einstein, the theory of motion, uniform motion. Quantum mechanics, a completely revolutionary theory of motion on the atomic scale. Now, those two theories were thought by Einstein and others to be almost certainly incompatible. They look completely different. They got different mathematics. That's the key thing. They look as though they're chalk and cheese, so to speak. But it is possible, and it's not easy at all, but it is possible to jam them together and come up with what's known as a fully quantum field theory. And that has been amazingly successful in describing the atomic world. Some of the most accurate predictions in physics have been made from the theory that combines relativity and quantum mechanics. Now, what physicists are doing today is using both relativity and quantum field theory, and in a generalization and development of that, what's called string theory, which again is based on quantum theory and relativity. So, contrary to the impression you might get from some quarters that physicists are sort of making up these weird and wonderful things and, you know, they're really disconnected from nature, I would argue that they are based very, very strongly on two of the best tested theories in the whole of science, namely quantum mechanics and relativity.
Now, when you say relativity here, you mean special relativity?
Well, at its most basic, yes. Yes, Einstein did generalize that theory to produce what he called the general theory of relativity, which is a theory of gravity. That is absolutely correct. Right? What I'm saying is here that at root, he had to generalize that basic theory. So I'm saying, to keep it simple, that simple theory of motion jammed together with quantum mechanics, right, has proved extremely fruitful. And I've got one classic example of that, which came from left field, was, of course, the great work of Stephen Hawking, where he took Einstein's theory of gravity, which has in it the prediction of black holes, where you have stuff where the concentration of mass is so great that even light can't escape. And he brilliantly found a way of doing a quantum mechanical calculation of that, and demonstrated that, as we now know, that black holes aren't completely black, rather they radiate, right? They behave like a thermal body, so to speak. Now, that doesn't mean to say that Hawking discovered a quantum theory of gravity. He didn't. But he showed that if you bring those two things together, you get amazing insights into nature. And most physicists take Hawking's work as if it were part of the curriculum, but it's never actually been verified. But I don't know any physicist who would deny that Hawking radiation exists, and almost certainly one day will be detected in some way.
Right. Well, I think part of why it's so appreciated is that it's seemingly inevitable consequence of just accepting both of those theories.
Yeah, exactly.
Yeah.
And as I say, the point is they take those two theories and they insist they're both right. It's amazing because I said you look at them when students first come across them, as it happened to me more decades away than I care to think about now. But you first think there's no way these theories are compatible. The mathematics are completely different, and it's incredibly difficult to do, right? But that is how the quantum theory of the subatomic forces was developed, right on a knife edge between those two theories. But it works. It works amazingly well. So, I think this is just absolutely amazing, and I think it's the way that physics is kept on track with those twin guide rails, so to speak.
Yeah, I agree. It was very interesting to read about that in your book. So, on a more historical note, which I like it, but I like science books that make it clear that science is a story of people. I think that's often forgotten, and that I think contributes to why so many students find it dry and dull. It's an exciting story of humans and egos and flaws.
Flawed, great, but flawed human beings.
Exactly.
We're all human. We all make mistakes.
Yeah.
And I agree. I think it's a good way of getting in to some quite difficult topics in science. If you could try to weave in, that's what I try to do in my book.
Yeah. Yeah. On that note, you talk about how basically following World War II, there was a quote unquote long divorce between the cultures of mathematicians and physicists.
Yeah.
So if you could reiterate, why did they separate during this period, and then what brought them back together in the 1970s?
Yeah, the phrase long divorce is Freeman Dyson's, and he's a great wordsmith, and it's a very graphic way of describing that physicists and mathematicians, certainly after the war, some people argue it was slightly earlier, but let's stick with Freeman Dyson and say after the war, they basically drifted apart like a dead marriage, so to speak, right? They could function better separately than they could together. That's how it seemed, right? Now, why was that? Well, as ever, one can diagnose these things in different ways. One factor which I think is very important is that there was a movement called Barkey began in France, which was very influential, which eventually sought to take the whole of mathematics and rebuild it bottom up from completely rigorous, clear, perfectly crystalline statements, so to speak, right, from the bottom up, totally paying no attention to applications at all. Right? Everything was based on the rigor of logic. Now, that was, I think, a necessary movement. I've spoken to mathematicians who said that was a very useful initiative, but it did take away mathematicians, move them away from close collaboration with physicists. Meanwhile, physicists were having a ball. They were actually making very good discoveries about the subatomic world. In particular, one physicist who died just a week or so ago, Murray Gell-Mann, he made, with relatively straightforward mathematics, he discovered some tremendous ordering in the subnuclear world. Right? There were discoveries in low temperature physics, in nuclear physics, all over the shop, but without the need for very advanced mathematics. As Freeman Dyson said, we just didn't think we needed mathematics. What brought them back together was that the territories came together in the early to mid 1970s. Now, what happened there was that the physicists found that this quantum field theory, this jamming together of special relativity and quantum mechanics, was the right way to describe the forces that shape atoms. This is the electromagnetic force that holds the electrons to the nucleus, and the weak and strong forces that hold together and govern the behavior of particles in the atomic nucleus. Now, the success of field theory, I remember because I basically was a kid, a researcher. It was an astonishing thing to see when, after a lot of debate about the kind of theory that would describe those things, it really did seem that quantum field theory was the way ahead. Now, what the great mathematician Michael Thier, he was, I think, fair to say, the leader in this field. He saw that those fields were rich with mathematical potential. They contained a lot of mathematical questions that he and his colleagues could benefit from. And the most famous collaboration, there are others as well, but when Michael Thier met Edward Witten in an office in the Massachusetts Institute of Technology, I think it was 1976 in the fall, that was a coming together between a great mathematician and a brilliantly promising theoretical physicist. And they and others started working together, and they found themselves on common territory. I might say Michael Thier is a friend of mine and a superb talker about mathematics and physics. He had a beautiful analogy which I wanted to share with you here. He was saying that the quantum field theorists were digging a tunnel, so to speak, in their own way, right, in their own field in physics, and making some success. The geometers, of which Michael was a great exponent, were digging a completely separate tunnel. What happened in Oxford when Thier went back and worked with Witten and other great mathematicians and physicists? Those tunnels intersected. And yet, what happened was, to the surprise of everyone, it looked like it was astonishing because they both had to start speaking the other's language, and the tunnels in Michael's language looked like they'd been perfectly engineered to cross, right? Which I think is a great image, right? That really started the coming together of physicists and and mathematicians, which continues to this day.
So the parties didn't end up getting divorced. They rekindled the romance.
They are. And it's funny, the physicist, Roman Jakif, it was in his office that Witten and Atiyah met. And he said to to Atiyah afterwards, do you think this will be a one-night stand or is this for real? And Michael said to me, it's been a long and happy, the coming back together of the marriage has been long and enduring. And at the moment, it shows no sign of having any great trouble.
Interesting.
I might say that it's quite funny there, because whenever you have this kind of thing happening between physics and mathematics, and you don't have the imprimatur of experiments verifying these things, you're going to have critics. And there are mathematicians who think that some of the mathematicians have been subverted, misled by physicists. And there are certainly physicists who think that some very, very good physicists have been misled by mathematicians. This is why, to me, I long for a time when nature speaks to us directly through experiment so that we can be sure we're on the right track.
Yeah, we'll see. And I'm going to ask you a little bit about that later, so I hesitate to follow up. So that's one historical trend in the 20th century that I found very interesting and I didn't know about. One other that I think I had heard briefly once before was that general relativity actually wasn't seen as a very promising field in the first half of this century, but now I think it very much is. And I think any student studying physics would certainly get the impression that general relativity is perceived as a quote-unquote big deal or significant. So what changed then?
Well, you're absolutely right that when Einstein came up with his general theory of relativity, this was, first of all, it was during the war, 1915, right? So the information flow from other countries was not great. And many physicists in other countries only found out about it after the end of the First World War. Now, quite a few people saw this as really, all right, a brilliant piece of work, but it's something you admire from afar, so to speak. Einstein was not, he explained some anomaly, he set up a beautiful theoretical construction, but it didn't seem terribly relevant to the kind of physics that people were really interested in particular atomic physics, which is what many, many people were working on. Of course, there are plenty of other types of physics as well. When general relativity took off after the war, you had mathematicians getting interested in mathematics as a theory. Some very fine physicists started to get interested in the mathematical form of Einstein's theory, but it didn't seem to be the hottest area. Right? It was, I think it's fair to say, pretty much a backwater. And Einstein, as we know, became semi-detached from the rest of the physics community when he rejected quantum mechanics as a fundamental theory of nature. What happened later was that owing to developments in technology, in astronomy, and some brilliant work, in particular by John Wheeler in the United States, Roger Penrose in Britain, and followed by Hawking's subsequent collaborator, Stephen Hawking, there was a renaissance in our appreciation that relativity was not just about fine effects, but could be about real things, right? Like black holes, for example, right? Which Einstein was not particularly enamored of them. I think he even was suspected they didn't exist, right? But people really started to think that they were real and you could do measurements on them. And earlier this year, we saw that amazing image that was the first ocular proof, so to speak, that those things really do exist. What's funny here is a lesson here that theoreticians have been working on black holes for decades, doing detailed calculations about them, right? So there's a real sense here that in the heads of the theorists and in mathematicians, they can investigate things even before experimenters discover them. And I think it just shows that our theory can get way, way ahead of experiment here. But you must always be kept on track by experiment. That's very, very important. Now we're in a wonderful time in cosmology and astronomy where, owing to these fantastic developments in telescopes and numerical simulations and what have you, that astronomers and cosmologists can really look back to the very early stages of the universe and to these exotic objects, gravitational waves. Fantastic discovery came out of Einstein's theory. So we opened up a whole new window on the universe. So general relativity now, as you rightly say, is hot, hot, hot.
So speaking of, maybe this is in the domain of general relativity, but you also mentioned in the book that the largest discrepancy we know of between experiment and theory right now is the energy of empty space.
Yeah.
The discrepancy is what, 10 to the 120 orders of magnitude?
It's absolutely incredible. I mean, that's my favorite fact. Actually, it's my favorite fact for any smug theoretician you come across. right? I'm speaking my tongue in my cheek, but it is a serious point. Probably the biggest discovery in basic physics in the last 20 years is the discovery by astronomers that the rate of the expansion of the universe isn't slowing down as you might naively think, and virtually everyone did think that, right? But is actually accelerating. Now, this was evidence for something called the energy of the vacuum, energy of empty space. And when you do a simple back of the envelope calculation of the energy of empty space using basic ideas of atomic physics, you get an answer that is 120 orders of magnitude out. So when you see people saying, "Oh, physics is great, it's the most wonderful thing, it's got these results here, agree to 11 decimal places," you say, "That's great, that's wonderful. But what about this discrepancy? This is 120. This must be the most inaccurate prediction that physicists have ever made about the Ulysses, as far as I know." And that in my opinion, that really does show that particular problem, understanding dark energy, the energy of empty space, right, is my candidate for the most pressing problem. And it's very few really good theories are tackling that head on. They think a better route to addressing that problem is to go to it indirectly. And one of the physicists here at the Institute for Advanced Study in Princeton said, "That's above my pay grade to go straight there." So they're looking for different ways to address the problem. But it's a huge challenge for physicists to understand that.
So do you think any of the theoretical developments that you write about in the book, string theory, supersymmetry, etc., do you think they could ever pave the way to solving this problem, or no?
I hope so. I remember all prognostications, predictions, or whatever about these theories, they always humiliate the person that makes them. I mean, even you go up to the very best people, the most brilliant people. I remember that the great physicist Steven Weinberg wrote a wonderful book called Dreams of a Final Theory, right? At a time when it really did look like physicists were going to pretty well wrap everything up once they had a very high energy collider and could look for the Higgs boson and what have you. And even he, they don't come any better than him. I asked him driving along a road in Austin, Texas, what did you think of that title? He said, "Well, maybe I was a bit premature there." Right? It really did look like we were gonna solve everything in terms of the basic forces of nature. But I believe that the basic symmetry mooted of nature supersymmetry, of string theory, of other developments will prove useful in the long term. What we're all waiting for, right, of course, is experimental guidance. And there's no getting around that. We've got to have that. We're not going to go back to natural philosophy and believe, along with Descartes, who's a great thinker, I know, but you really could have a kind of narrative philosophy of nature. We want it anchored in comparisons between mathematical theories and the best numerical experiments we can do.
Mm-hmm. Yeah, for sure. I agree. Although, who knows where those experiments come from? I mean, it could be that we're just barking up the wrong tree entirely.
I doubt that. It's a free country. You could say that. I very, very much doubt that quantum mechanics and relativity, to go back to it, will have taken us to a completely wrong tree, right? We will see. I personally very, very much doubt that.
Mm-hmm. So we talked a lot about the different theoretical developments and the role of experimentation and what it should do. You also write about, and largely talking about Dirac as well, you have a quote in your book that someone said, "Whenever physicists do a long and complicated mathematical calculation, a surprisingly simple result is often a powerful indication that they could have derived it more elegantly."
Yes.
In addition to theory and experiment, why is it, do you think, that elegance seemingly does play a role in either guiding us to the quote-unquote correct theories, or just that it plays a role in our theories to begin with?
Well, I have no idea about that, and I'm not being evasive. It might be two questions in what you're talking about there. There's an elegant mathematical structure, right? And I have no idea why that is the case, right? I would embarrass myself by saying I doubt that will ever be understood, but maybe I'm wrong. But you're talking there about something that is experienced by physicists routinely in their careers, where they do a calculation and it's a long, involved calculation that comes down to a very simple answer. Very often it's because they've missed something. They've missed a smarter person than them, perhaps, or some other ingredient they missed will simplify things. Now, there's a classic example of this, an absolutely wonderful example that comes from the field that is now known as scattering amplitudes, where you look at the scattering of tiny subatomic particles called gluons. They're the particles responsible for the forces between quarks. Now, you do a calculation of the scattering between two gluons of a certain type of scattering at very high energy. And to do that calculation will take you hundreds, sometimes thousands of pages. And those thousands of pages will take you, in the end, to a formula you can write on a palm of a hand. Right? Now, those are the state-of-the-art calculations using our best theories. Now, that is something that leading physicists think is nothing to do with the elegance of mathematics. It's we're missing something here. There's something wrong with the way we are setting out this theory. Now, that observation made in the 1990s has really encouraged people to look at the way we talk about the scattering of quarks and gluons, and encourage people to think that we may be looking at it in the wrong way. Right? Now, that, you see, is a different kind of clue. It's not just about the theories at the top level. It's saying that we're just addressing this in the wrong way, right? So, and again, I know people are very, very encouraged by that line of research. And you're right, though, that it's not a case of this must be the way ahead, but it feels like a very strong indication that we're missing something.
Right. In other words, scientists are sort of guessing, rightly so, I think, that reality is more elegant than our dirty calculations at the moment.
Well, yeah, nature doesn't do calculations, of course, it just is.
Right.
But when our calculations stretch to hundreds or even thousands of pages, you think, is it really necessary to do that, or are we missing something?
Yes, that's what I mean.
Yeah, sure.
Okay. Towards the end of the book, you very compactly list 6 ideas that, while not yet corroborated by experiments, you do expect to withstand the test of time. So you do predict the future and hopefully not humiliate yourself.
Well, I have to say, if you look at my language there, I say that if you really make hard predictions, you're going to be humiliated. And yes, it is true. I suppose I am risking it. But what I was doing there was I really find it upsetting when people talk about many hundreds of physicists who are doing great work as if they're just making it up on the hoof, right? And that it has no substance. I believe there's very good reason for believing there is something in this. And I wanted to put there some concrete things that could happen in the future that would demonstrate progress. That's what I was trying to do. If you ask me to bet, will all of those 6 things be verified in my lifetime, or right? Then no, probably not, right? But I simply wanted to show that there are things that the physicists do think about the real world, right? And there are reasons to believe that we're going to see them. So it was slightly more modest than a tub thumping declaration of it. But anyway, I just wanted to be clear about that.
Yeah, for sure. Which of the 6, if you had to bet, which of the 6 will withstand the test of time? If you were just a betting man and you had one of the 6, and why?
Well, I believe that there are things called magnetic monopoles that were envisaged in the 19th century. The first quantum theory was discovered by Paul Dirac. There's now a more advanced theory. It's now embedded in the theory. I believe that magnetic monopoles really do exist. So you know that when you're back in high school, everyone is taught there's a North Pole and a South Pole. Poles come in pairs. But physicists believe that they can exist in isolation. There's a North Pole on its own or an isolated South Pole, right? And I believe that they will be discovered and that we will be seen to have a serviceable theory of them. But it's not going to be straightforward. But I would bet a reasonable sum of money, but it may be that I'm not, I would have shuffled off this mortal coil by the time they are discovered. But that's one really clear, solid example of something that's been looked for but not found yet.
Mm-hmm. All right, so I have you on record. Magnetic monopole.
Okay, well, yes, that's rather annoying because I can't change that off.
Yeah.
Okay.
Only teasing. You also write toward the end of the book that the slow rate of progress of the framework of string theory might presage a more sedate pace in fundamental physics that may persist for a while. You even say maybe for centuries. So could it be that, well, I already asked you a little bit about this earlier, but could it be that physicists are just focusing on the wrong paradigm altogether, and that there's just something fundamentally wrong with the strategies that are currently being employed?
Yeah. Well, again, you're asking me to be a clairvoyant, and I don't blame you. But you have to say, your question is slightly rhetorical, because you're daring me to say that we are definitely right. if you ask me, are we missing something? Then my hunch is pretty well definitely. I mean, I'm absorbing this from much smarter people than I am. It could be that we are like physicists at the end of the 19th century, right, who saw that in the very closing years of that century, that energy is quantized. It comes in quanta. Now, that began the quantum theory revolution, something that is just not part of the Newtonian structure. Now, could it be that there's something as fundamental as that missing? Why not? Why not? You're one is a fool to rule out that kind of thing out. My belief is that what the thing that is tough for many people to absorb, to come to terms with, is for decades, fundamental physics, the physics of the atom, for gravitational physics, especially of late, they've made such incredibly strong progress. I mean, I remember when I started as a student, these discoveries were coming, it seemed to me, every few months. It was incredible to be part of this. Experimenters had come with these great findings. Theoreticians were arguing constructively among themselves and with experimenters about what was real, what was fake news, so to speak. In other words, a discovery that was evaporating. It was a wonderful thing to be even at the back of the stalls, which is where I want to see this take place. Now we're in a different world. You see theoreticians who never make a prediction with experiment. You even see experimenters who get PhDs on simulations without doing any actual experiments. We're looking at a different pace where things take a lot longer to set up these huge projects, whether astronomical or big particle colliders. And I suggest at the end of my book that I suspect that things may become more and more challenging here. Things get more and more expensive. They take longer to set up, and there will be long periods in which experimenters have to tool up, so to speak, and theoreticians don't have a flood of new clues, right? They may come every, say, 10 or 20 or 30 years, but instead have to mine the mathematics, which takes us back to that early theme. When you get the best theories you can and explore their consequences in terms of developing their mathematics. So I think we might have to get used to progress that's been a good deal slower than the feast that we saw 40, 50 years ago.
Yeah, it'll certainly be interesting to see how this all plays out in the coming years.
I agree.
Okay, so I have one more question that does not require clairvoyance. You write about the sort of famous phrase, the unreasonable effectiveness of mathematics and physics.
Yeah.
But you also very much go into the converse, which I had never heard this before, the unreasonable effectiveness of physics and mathematics.
Yep.
What do you mean by that? And could you give us some fun examples?
Sure. Well, that, as you rightly say, that mathematics is a wondrous tool for physicists. Even at high school, you start to see how you use basic maths to account for experiments, right? And that works all the way right up to the superstar physicists that use mathematics. What has been so striking since the early 1970s is that the intuition you get from the geometry that arises out of physics are amazing insights into mathematics. So here, the great mathematician Pierre Deligne, he who has worked with some of the physicists here, he said he would dearly love to do without the input of physicists. He wants mathematicians to be self-sufficient, but he just can't do it. He constantly finds stimulation from string theory, from scattering amplitudes research that we see, that helps him. And indeed, he's by no means alone. There are thousands of first-class mathematicians doing this, that helps them to deliver their abstract ideas. That, I think, is something that is here to stay. I mean, I've never known pure mathematics and physics be closer in my lifetime.
Yeah, that was a very cool idea to hear.
It is. But why? Dirac wrote in 1939, perhaps very far-sightedly, that he said it was a bit fanciful, but he one day suggested that subjects might unify. That would be an astonishing thing. And then maybe further than that is, why do they unify? And that's way above anything I can speculate about. But it's incredibly exciting.
I agree. Okay, so is there anything that you think the reader should know that I didn't ask about?
Yeah, sure. I'd like, if I may, I found a way of introducing this topic from the bottom up, so to speak, that I think is quite useful. Einstein was a philosophical thinker as well as theoretical physicist, and he wrote in 1952 that the central miracle was that our universe is ordered. There is an underlying order to this teeming, seemingly chaotic universe, and that we can discover that order at the heart of the universe. Now, those patterns are the work of physicists. That's what they're trying to do. They're trying to understand patterns among all the different measurements that they make, trying to understand how the different things are linked. Now, mathematicians, they also study patterns. As G.H. Hardy said, they're looking at patterns of ideas. What we find then is that the patterns studied by the mathematicians are incredibly useful at understanding those patterns that we find in nature. So that's essentially why the physicists and mathematicians work together. They're both fundamentally interested in patterns. Now, what we see today, we have these gorgeous patterns manifest through what we call the best laws of nature that we have, and they use the patterns that mathematicians identify. Now, while we're looking to extend the patterns of nature, we find it's useful to work with the mathematicians on developing the patterns of ideas that they have. I think your people would find that, I hope your listeners would find that an introduction, into why those two things come together. I conceived of writing this book, The Universe Speaks in Numbers, here in Princeton. And a lot of it there was two reasons really. One of them is that I thought when I was a student that the ultra mathematical approach to physics was going to go away. It was way overdone, that it would peter out. And I've been proved completely wrong. It's flourished. And I wanted to understand why that is. And secondly, I wanted to understand or come to grips with some of the ways in which mathematicians and physicists can't do without each other. They really do need each other's input. And I wanted to try to understand how we came to that situation from a historical perspective, beginning back in Isaac Newton, going to electromagnetism in the 19th century, right up to the present day, and try to tell one coherent story about that astonishingly symbiotic relationship between physicists and mathematicians.
Yeah, I think you did a great job. I really enjoyed the book.
Good. Okay, well, I'm very glad you did. And thank you. And lots of good questions. I hope I've given you something you can use there.
Yeah, absolutely. I really appreciate your time. It's been a lot of fun.
Feel free if you want to get in touch. I'm very happy to help if you wish.
Thank you very much. Have a great day.
All right, take care. Good to speak to you. Bye-bye.
Yeah, you too. Bye.
Bye.